Welcome back to the Deep Dive. Our mission here is always to take the world's most complex technical blueprints, strategic roadmaps, and research papers, and really distill them into actionable strategic knowledge for you.
And today we have a fantastic one.
We really do. We are strapping into the driver's seat of, well, perhaps the most profound industrial shift happening right now. The revolution in intelligent driving.
It's massive. And this isn't just about, adding a few autonomous features to a car.
Not at all. It's about fundamentally reshaping transportation on a global scale. And it's all powered by an incredibly aggressive, quantified blueprint, what's being called the Intelligent Driving Technology Roadmap 3.0.
And this is exactly the kind of document we love to dig into. What we're looking at is, it's essentially a highly detailed consultancy-style report. It's a strategic analysis that lays out the necessary leap forward.
So our mission for you, the listener, today is not just to catalog a list of goals.
No, it's to deeply understand the core architectural shift that's driving this entire effort. We're talking about the move from these sort of clunky, modular rule-based systems to a unified, data-driven, end-to-end, or E2E, AI architecture. That's the key.
And we're not talking about general aspirations here. This roadmap is extremely quantitative. We are going to be breaking down the specific, and I mean highly ambitious, technical targets set for 2030, 2035, and 2040.
We have to. We're going to quantify the shift from, say, L3 and L4, conditional autonomy, all the way to what they're calling L5, superhuman performance.
So we have to move beyond all the marketing hype.
Oh, absolutely. We need to analyze the technical key performance indicators, the KPIs. That's what defines success here and reveals the true competitive landscape.
Okay, let's unpack this, starting with why intelligent driving holds such immense strategic significance. I mean, it's got to be more than just making your commute slightly less tedious.
Yeah.
So the sources we're looking at position intelligentization right up there with electrification. They're calling them the two massive global transformations that will define the next century of mobility.
They are.
But we often think of autonomous driving as, a product feature. The sources call it the core new engine driving industrial upgrading and technological evolution. That's a pretty big statement. Why the elevated status?
Because the impact is truly societal. It reaches far, far beyond the vehicle itself. I think the most immediate and, frankly, the most critical societal impact is on safety.
Right, the human error factor.
Exactly. Statistically, something like over 90% of all accidents are caused by human error. By implementing advanced automation, and especially by integrating it with V2X, that's vehicle-to-everything communication and smart traffic management.
What the roadmap calls car-road cloud integration.
Precisely. You can drastically reduce that margin of error. So the long-term goal isn't just to save a bit of time on your commute. It's to save hundreds of thousands of lives globally every single year.
And it makes sense that if you reduce that chaos, you naturally boost efficiency. When all the systems are talking to each other, they can optimize the flow of traffic.
That's the next pillar, efficiency. This capability translates directly into alleviating chronic urban congestion. Think about optimizing road resource use in real time.
No more phantom traffic jams.
Hopefully. This kind of sophisticated orchestration directly supports the construction of future smart cities. It dramatically improves logistics chains, public transit efficiency. It really elevates the entire social operational efficiency and cuts down on the massive economic drag that's caused by gridlock.
And that structural efficiency, that also ties directly into the green transition, which the sources highlight as a major strategic goal. How does intelligent driving help with something like achieving dual carbon goals?
It's all about enhancing operational efficiency and precision. An intelligent system, especially one that's integrated with new energy vehicle technology, can manage the energy demands of a vehicle far, far better than a human can.
So no more aggressive acceleration or hard braking.
Gone. It can optimize route planning based on energy needs, coordinate vehicle dispatch for fleets. This precision scheduling reduces overall energy consumption and resource depletion. It's a crucial systemic contribution to sustainability that we often forget about when we're only focused on, say, battery technology.
Okay, so moving from those physical, societal goals to the technological ones. The roadmap emphasizes that intelligent driving isn't just consuming AI, it's actively accelerating the development of foundational AI itself. How is that possible?
Because high-level autonomous driving is fundamentally driven by breakthroughs in advanced deep learning and machine learning, particularly for those three core functions: perception, decision, and planning.
And the unique mechanism here is what they call the data closed loop.
That's the engine of progress. You have these vehicles operating 24/7 in infinitely varying real-world conditions, collecting massive amounts of high-fidelity driving data. That data is then fed back to continuously optimize and train the underlying algorithms.
So intelligent driving effectively acts as the world's most challenging real-time AI laboratory.
Exactly. The demand for real-time, robust, and generalizable AI that can handle physical reality. It pushes the boundaries in adjacent fields, things like natural language processing, which needs to understand complex human intent, and especially computer vision. The constant need for more efficient and faster models just accelerates AI progress across the board.
And that technological demand creates this enormous cross-domain synergy. I mean, the tech required for this just spills over into other industries.
Absolutely. The need for advanced sensing technology, we're talking millimeter wave radar, high-res cameras, LiDAR that translates directly to drones, to robotics, sophisticated security systems, even medical imaging.
And what about the brains of the operation?
Yeah.
The computing power?
Well, the sheer computational requirements for these autonomous platforms drives innovation in high-performance computing. It demands extreme efficiency, which is measured in TOPS per watt. That's tera operations per second per watt. We need chips that can process trillions of operations while staying cool inside a small vehicle enclosure.
And the communication backbone, that V2X requirement for high bandwidth and super low latency, that accelerates the rollout of network infrastructure globally. It's an entire ecosystem being pulled forward.
That's the key takeaway right there. Intelligent driving is the technological flywheel that just spins faster and faster, pulling adjacent sectors from silicon manufacturing to telecommunications right along with it. Hashtag 1.3 the flaw in the old plan, RoadMap 2.0.
Okay, now, let's look at the past to understand why this radical revision, RoadMap 3.0, was even necessary. The sources say that many of the 2025 goals from the previous blueprint from 2.0 were actually met.
They were. Things like 4D radar detecting objects over 350 meters away, or decision performance reaching about 90% of a human level.
So if they met these big markers, why the need for a total architectural overhaul? It sounds like they hit a technical ceiling on the really hard, the life or death stuff.
They absolutely did. The successes of 2.0 were largely achieved through, let's call them incremental improvements within a fixed modular architecture. But two critical interconnected constraints prevented that next big leap toward truly complex, ubiquitous autonomy.
What was the first technical bottleneck?
Latency. Even by 2024, the perception calculation time in high-speed scenes was stuck. It was hovering around 80 milliseconds.
And the goal was much lower.
Much lower. The initial goal was to get that into the single digits, a target they missed significantly. And this delay is so critical because at highway speeds, 80 milliseconds can equate to several meters of travel before the system has even finalized its understanding of a dynamic threat.
So the system was seeing the world, but the time it took for that decision to actually reach the steering or the brakes was too long to react optimally, especially in an emergency. Is that just a chip issue, or does the architecture itself, that separation into perception, then decision, then planning, contribute to the delay?
The modular architecture is a huge part of the problem. When data has to pass sequentially from a perception module to a decision module and then on to a planning module, each one of those steps adds processing time, complexity, and potential for cumulative error. You have to wait for Module A to finish its job before Module B can even start. That separation itself introduced bottlenecks that were just impossible to solve incrementally.
And the second flaw, this one addresses the chaos of the real world, the infamous long-tail scenarios.
This was the bigger systemic failure. These are the rare, complex, and unpredictable driving situations. Think of a complex, temporary construction zone. Now combine that with heavy rain, low sunlight, and an unexpected pedestrian carrying some unusual object.
Things you can't possibly pre-program for.
Exactly. The older modular systems, which rely so heavily on explicit rules and pre-labeled data, they perform terribly in these combinations. They struggled because acquiring and labeling the real-world data for these rare, critical events is incredibly expensive, and a lot of the time, it's impossible until the event actually happens.
Oh, the classic problem. You can't program for every contingency, and you can't collect enough data for that 1 in a million scenario that could be fatal.
Precisely. RoadMap 2.0 relied way too much on explicit human design and brittle rules rather than the system's ability to generalize and learn on its own.
Here's where it gets really interesting. This shift isn't just an upgrade, it's a total architectural revolution. The solution to both of those fundamental problems, the latency and the long-tail scenarios, is the heavy integration of large model technology and an immediate pivot to end-to-end autonomous driving.
Yes, alongside prioritizing that car road cloud integration infrastructure we talked about.
So this is the big change.
Absolutely. The 3.0 revision mandates this strategic pivot. The end-to-end architecture, it bypasses those brittle, handcrafted interfaces between the old perception, decision, and planning modules. By using these large, unified neural networks, the system can map raw sensor input directly to a control output.
Which would have to reduce latency.
Inherently, it streamlines the whole process. And it's intrinsically designed to enhance adaptive capability in complex dynamic environments, which makes it far more capable of handling those long-tail scenarios through generalization rather than just, rote memorization.
Okay, so to understand the implications of this huge shift, we have to put it in context within the global race. The sources paint a pretty clear picture of a tripolar competition: the US, Europe, and China.
That's right. And each major player is leveraging its unique strategic assets and, of course, facing very distinct risks.
So let's analyze their strategies. The US approach, which is really spearheaded by companies like Tesla and Waymo, seems to be defined by algorithm innovation and computational power.
It is. They pioneered the high-compute, data-driven approach, utilizing paradigms like BEV, that's a bird's eye view, and transformer models for perception, often paired with occupancy network concepts.
So their advantage is clearly in the software and the raw compute muscle.
Yeah.
Heavily reliant on high-end chips, which, let's be honest, is a market dominated by NVIDIA. What's the long-term risk of a strategy like that?
Well, the risk for the U.S. model is its reliance on sheer data scale and the potential regulatory headwinds that come with it. If data privacy or acquisition methods face increasing international scrutiny, or if their approach to E2E, which often lacks a bit of transparency, hits liability walls.
The innovation cycle could stall.
It could. However, for now, they currently have the lead in generating and deploying true data-driven E2E solutions.
Now, Europe's strategy seems much more conservative in comparison. They're prioritizing standardization and reliability.
They are. Europe, led by the major German manufacturers, really emphasizes high reliability and standardization. Their approach typically involves multi-sensor fusion. They often place a very high value on LiDAR for redundancy, and they build highly modular, high-reliability decision systems. Their focus is on regulatory compliance and setting global standards through protocols like OpenDrive and OpenScenario.
So while they might be slower to adopt the full E2E AI revolution, their systems are really built for long-term robustness and, I imagine, legal clarity. What's their risk?
Their risk is falling behind in the AI arms race. By prioritizing modularity and explicit rules for safety, they might struggle to generalize their systems rapidly enough to handle the sheer diversity of global long-tail scenarios. They could potentially cede technological leadership to those who are embracing the E2E paradigm more fully.
And finally, China's position. The roadmap suggests a focus on rapid scaling and fusion application.
China has a unique strategic asset here: its vast market scale and the incredible complexity of its road scenarios. This provides a really unparalleled training environment for data collection.
So they have the perfect test bed.
They do. They're rapidly closing the algorithm gap and have shown explosive growth in E2E implementation just this year in 2024. However, their constraint is geopolitical and technical. They still face a reliance on foreign suppliers for core components, specifically those high-end chips and certain advanced sensor technologies.
So the strategic goal of this Roadmap 3.0 is to leverage their data assets and their scaling capability to overcome those component constraints and achieve really technological autonomy in the entire stack.
Exactly. It's a race to scale the data closed loop faster than the competition can restrict access to the core hardware. Hashtag 2.2 status quo in core subdomains as of 2024.
Okay, so let's look at the current status across these core subdomains.
Yeah.
We can compare the 2024 performance against those now defunct 2025 goals from Roadmap 2.0. Let's start with environmental perception.
Okay. The global trend has moved decisively toward complex, real-time environment parsing. So instead of just, identifying a car or a pedestrian, the system needs to understand the 3D space and predict object behavior. That's the BEV plus transformer and occupancy network approach.
And how are they doing on the old goals?
The good news is the 2025 goal of obstacle detection range exceeding 350 meters. That's been met and surpassed. Performance is now reaching 400 meters.
A clear check mark on detection range. So where's the shortfall in perception?
It's in recognition accuracy. The 2025 goal was greater than 90%. As of 2024, the observed obstacle recognition accuracy is only around 78%.
And that 12-point gap is huge.
It's critical. Achieving high L4 and L5 autonomy demands nearly perfect perception because any error there cascades directly into a catastrophic planning error. This is why the new focus is on occupancy grid prediction, creating a dense, detailed map of the environment, where scores are improving fast but still require significant R&D.
Okay, next up, decision and planning. The intelligence that decides what to do. This is where those data-driven methods are really taking over from the old rulebooks.
This domain is seeing some of the most exciting breakthroughs. The shift is unmistakable, from those modular, rule-driven systems to the data-driven approach, which is really exemplified by Tesla's FSD V12.
And in China.
In China, rapid progress is evident with platforms like Baidu Apollo and Huawei's Qinaziji achieving over 90% decision accuracy in typical highway and main road scenarios. The 2025 goals for key behaviors, things like following, lane keeping, changing lanes, at 95% correctness have been met.
And what about that latency issue from RoadMap 2.0? How's the current speed of decision-making?
The trajectory calculation update cycle has met its 2025 goal. It's sitting in the 50 to 100 millisecond range. Now, this is adequate for conditional automation for L3, but it's really insufficient for truly robust L4 or L5 in high-speed dynamic environments, which is why we have to talk about the architectural change itself.
Right. Let's discuss end-to-end driving the architectural revolution. Can you define E2E driving for us, especially in the context of latency and generalization?
E2E is fundamentally a simplification and a unification. It's defined by a fully neural network architecture that takes raw sensor input, whether that's camera pixels, radar returns, or LiDAR point clouds, and it maps it directly, without any of those intermediate modular steps, to vehicle control outputs. So steering angle, brake pressure.
And that structural simplicity is what cuts the latency.
It inherently reduces latency, and it achieves stronger generalization because the model learns to correlate inputs and outputs across literally billions of driving miles.
An architecture like that must require massive AI models. Who's pioneering this globally?
Well, Tesla's FSD V12 and now V13.2, they remain the international benchmark. They really showcase the power of increasing parameter counts and utilizing time series inference. Importantly, Waymo has also demonstrated the use of a system called EMA, which incorporates multimodal large language model components to address a major E2E flaw, transparency.
So they're trying to open up the black box.
Exactly. They're using the LLM to provide some level of interpretability, turning that black box into a slightly more understandable system.
And we heard about the explosive growth in China for E2E development in 2024.
Yes, and this signals a unified commitment. Mass production applications are rapidly appearing from players like Huawei, XPeng, and Li Auto, alongside foundational research breakthroughs like the UniAD model. The consensus across the entire competitive landscape is that E2E is really the only path forward to overcome the limitations of that 2.0 architecture.
But the sources state that the biggest constraint for rapidly scaling this E2E architecture is infrastructure. What exactly is that infrastructural gap?
The constraint is the need to construct a robust, industrial-scale data closed-loop system. The E2E architecture is a data-hungry beast that requires continuous high-volume feeding. Compared to the foreign leaders, there is a recognized struggle with obtaining the necessary quantity and, crucially, the quality of data needed for training truly generalizable cross-scenario systems.
So it's more than just collecting miles.
So much more. This requires advanced systems for data collection, for automated labeling, for massive scale simulation, and industrial-grade distributed training clusters. That infrastructural deficit is the core focus of the strategic investment outlined in RoadMap 3.0.
Okay, finally, let's touch on testing and evaluation, the safety backbone. If we can't test it, we can't deploy it. Where do things stand in 2024?
Initial progress has definitely been made. The total test mileage exceeded 38.93 million kilometers in 2023, and they have established initial tool chains and evaluation frameworks. Tool chains include systems like PanoSim and in Lab Sierra Hill, which is hardware in the loop.
Right, a common setup for testing physical vehicle components against simulated environments.
Exactly. And evaluation frameworks include iVista and CICAP, which are domestic safety certification protocols.
So the roadmap highlights two major areas where they're lagging internationally.
That's right. First, the scale and complexity of the testing scenario library are inferior, particularly the accessibility of complex open-source data that reflects that long-tail problem. Second, There's insufficient autonomy in core testing hardware and software tool chains, which are still heavily reliant on established international providers like NI, which is National Instruments, or DSpace.
So even as the algorithms themselves become cutting edge, the tools used to certify their safety remain dependent on others. The 2025 goals were to reach tool chain self-sufficiency of 30% and scenario coverage rate of over 80%. Meeting those is vital, but the strategic push for 2040 means they need to aim far, far higher. So we've established the current status and the big strategic pivot. Now we can move to the core of this consultancy report, the 2040 vision. This is the quantified roadmap showing the path from those L3, L4 breakthroughs all the way to L5 transcendence, hashtag tag 3.1, the 2040 grand vision, the 4 pillars.
Right. And the 2040 Grand Vision is built on 4 core pillars that define what the ideal future transportation ecosystem should look like.
Starting with the foundation, safety and efficiency.
And the goal here is not just incremental improvement, it's transformation. It's to substantially reduce accidents and injury rates and to greatly boost traffic and city operational efficiency, using data-driven methods to achieve a level of reliability and speed that fundamentally surpasses human capability.
And the next pillar deals with the user experience, redefining the vehicle itself.
This is the harmonious and comfortable pillar. Full autonomy means freeing the driver, transforming the car into a smart mobile space for socializing, for entertainment, for work. This really speaks to the qualitative shift that's enabled by L4 and L5 systems. The car becomes a movable extension of your home or your office.
Then there's that environmental link we discussed earlier.
Green and healthy deep integration with new energy vehicles to optimize energy and resource consumption. This is where intelligent logistics and efficiency play a crucial role in managing the energy grid and vehicle fleet sustainably.
And finally, that large-scale economic multiplier effect.
Industrial integration. The goal is to leverage intelligent driving as a strategic technology engine, driving technological upgrading across the entire automotive supply chain, from raw materials and sensors all the way to high-performance computing and software deployment.
Okay, this is where we get highly specific. Let's break down the quantifiable goals, focusing on the sheer magnitude of the required leap in reliability. We'll start with 2030, the near-term focus, which is aiming for L4 breakthroughs.
The 2030 target focuses on achieving performance that approaches human competence in most common scenarios. It's about demonstrating the initial reliability of the E2E architecture.
Let's look at the safety KPI for 2030. Highway intervention or takeover rate of less than or equal to 3 times per 10,000 kilometers. The city intervention rate is less than or equal to 30 times per 10,000 kilometers.
Right.
To give our listeners some context, what is the rough failure rate of an average human driver in those complex city scenarios? Is 30 per 10K kilometers already better than the average person?
That's an excellent question. Studies show that human drivers make tons of minor errors per kilometer, but the rate of critical interventions errors that require a sudden or aggressive maneuver to avoid a collision, that's much harder to quantify globally, but it's certainly much higher than 30 per 10,000 kilometers in congested environments.
So this is already a high bar.
It's a demanding industrial-grade benchmark for L4 reliability. A rate of 30 interventions per 10K kilometer suggests the system is operating at a consistently reliable, cautious level, likely surpassing the average human driver in vigilance, though maybe not yet in creative, complex maneuvering.
And what's the corresponding requirement for decision performance by 2030?
The goal is for the intelligent decision ability to reach 95% of a human driver's level, operating well in 90% of common scenarios. This means the E2E system must have been trained robustly enough to handle common traffic dynamics, merging standard intersection navigation with near-perfect competence. Critically, E2E products should achieve initial industrial application at this stage.
And the sheer infrastructure required to train these initial E2E systems for 2030.
Well, by 2030, the L4 testing ecosystem must be complete, and the KPI for total road test mileage is a staggering minimum of 1 billion kilometers.
A billion.
That is the minimum data volume required to feed the first generation of industrial E2E models and start verifying their safety across those 90% of common scenarios. On top of that, test scenario coverage has to hit at least 90%, and testing tool self-sufficiency must reach 30%.
All right, let's move to 2035. This is the midterm focus, aiming for global leadership, and this stage demands an exponential leap in reliability.
It truly does. The 2035 goal is not incremental, it's transformative. Just look at the safety targets. The highway intervention rate has to drop to an extremely low figure of less than or equal to 0.3 times per 10,000 kilometers.
That's a tenfold improvement from 2030.
A tenfold improvement. And city intervention rates must also fall to less than or equal to 3 times per 10,000 kilometers.
How does one even achieve a tenfold improvement in reliability in just 5 years? Is that all based on the data closed loop? Or is there a hard architectural requirement?
It relies on both. You can't get that kind of reliability jump just by tweaking code. You need the scale of the data closed loop to identify and eliminate those rare failure modes, the long tail, and you need the architectural shift of E2E using large models to enable better generalization. The sources confirm the architectural requirement. E2E model parameters must reach at least 20 billion by 2035. That signifies the mandatory use of true, massive AI foundation models optimized for driving.
And the corresponding leap in intelligence.
The intelligent decision ability target moves up to 98% of the human driver level, operating well in 98% of common scenarios. And critically, the expectation for E2E performance at this stage is that it is equal to or beginning to surpass the human level.
And the testing and validation infrastructure must provide 5 times the data accumulation.
Absolutely. The total road test mileage must hit 5 billion kilometers by 2035. Testing tool self-sufficiency has to reach 50%, reflecting a necessary increase in independence for core validation tools. This is the infrastructure that supports the commercialization of fully intelligent vehicles in major markets.
Okay, finally, the 2040 long-term focus, achieving superhuman performance. What does that look like in pure safety numbers and technological capability?
This is the definitive endpoint. The sources state the safety level must far surpass that of a professional driver. Highway intervention rates must be reduced to less than or equal to a 0.1 times per 10,000 kilometers, or potentially a system disposal rate of 0.01 per 10K kilometers. City intervention rates must be below 1 time per 10,000 kilometers.
So failure becomes an extreme anomaly.
Exactly. This implies near-perfect L5 autonomy and the required intelligence. Decision capacity must explicitly surpass the human driver. Environmental recognition accuracy should reach 99.9%. Furthermore, this stage requires the full realization of car-road cloud integration to achieve comprehensive, ultra-safe redundancy. And the accumulated data scale target is 10 billion kilometers of test mileage. That's the scale of data required to train the models that can handle truly infinite variables.
So the roadmap shows this clear trajectory from approaching human level in 2030 to matching or slightly surpassing it in 2035.
To being objectively and statistically safer than any human professional driver by 2040. The shift from 30 interventions per 10K kilometers to just 1 intervention per 10K kilometers is a reliability improvement of 30-fold. This is the difference between an early cautious pilot program and a globally indispensable commercial L5 system. So to understand how these monumental goals can be achieved, we have to break down the core technological pillars that underpin the entire roadmap. These are the specific areas where massive R&D focus is required.
Okay, let's start with perception. We've established the current constraint is acquiring data for those rare long-tail scenarios. How is the roadmap addressing this data challenge, which is so critical for E2E generalization?
The solution is a strategic pivot. It's a move away from sole reliance on costly real-world collection toward leveraging generative AI high-fidelity data. Think of companies like Waabi or NVIDIA that are pioneering the use of large generative models to create synthetic, highly realistic, and customizable driving scenarios.
So they're manufacturing the data they need.
Exactly. This allows systems to be trained on millions of variations of a complex construction zone, combined with specific weather conditions data that might take decades to collect organically. This generative approach dramatically reduces the cost and complexity of solving that long-tail problem.
That's a fascinating application of generative AI. And perception is also moving beyond just the vehicle itself.
Right. Vehicle perception is evolving toward car-road cloud integrated sensing, V2X. This means utilizing external data from roadside units, from traffic management systems, and from other vehicles to provide a kind of super sensing capability, ultra-long distance perception, and essential safety redundancy that a single vehicle sensor array just cannot achieve on its own.
What are the specific hardware and algorithm trends that are required to hit those 2040 targets?
On the hardware front, the roadmap calls for high-resolution, low-cost LiDAR. It specifically mentions MEMS technology, that's micro-electromechanical systems, which offers solid-state reliability and the affordability that's necessary for mass-market deployment. We also need enhanced cameras with high dynamic range, HDR, for handling low light and complex glare, and 40 millimeter wave radar for robust all-weather detection.
And algorithmically.
The evolution is toward occupancy grid prediction. We're moving from coarse object boxes to a fine-grained, volumetric understanding of all obstacles and all free space.
The 2040 performance goals here are just massive.
They represent an exponential leap. The current detection range of 400 meters, that needs to be extended to over 1,200 meters by 2040. You only get there with car road cloud integration. Recognition accuracy must reach an almost perfect 99.9% or higher. And crucially, the system has to overcome those initial latency failures. City calculation delay needs to be 30 milliseconds or less, and highway delay must be lightning fast at 20 milliseconds or less. That level of responsiveness is just non-negotiable for L5 safety.
Okay, so decision and planning is the actual brain of the system. The sources talk about achieving superhuman intelligence through a third-generation intelligent decision architecture. What does that fusion look like?
It's the organic fusion of rule frameworks and data-driven models. The industry realized that the purely rule-based approach of the past was just too rigid. However, a purely data-driven system can sometimes lack explainability or adherence to fundamental traffic laws. The third-generation architecture integrates the generalization power of AI with a framework of traffic rules, which provides necessary safety boundaries and improves transparency.
And large models, LLMs, are the engine for this required generalization.
Exactly. They allow the system to learn complex, human-like driving behaviors based on billions of parameters. We're talking models like those estimated in Tesla's FSD V12, around 3 to 5 billion parameters. The integration of LLMs like XPeng's XPlanner and XBrain enhances the system's ability to reason, predict human intent, and navigate complex social interactions in traffic, which makes the vehicle behavior both safer and more comfortable.
But integrating models that complex has to introduce significant technical and, I imagine, ethical challenges. What are the remaining hurdles?
The immediate challenges are threefold. First, data scarcity for the truly rare unseen scenarios remains difficult to completely solve, even with generative AI. Second, there is a persistent and major issue of the black box problem.
Right, not knowing why it made a certain decision.
Exactly. The complexity of the neural network reduces transparency and interpretability. You don't know why the AI chose to swerve rather than brake. This is a huge legal and engineering challenge. And the third hurdle is the crucial lack of standardization for L3 liability and policy, covering things like ethics and data privacy. Until these global policy frameworks are clear, fully deploying systems that make complex, uninterpretable decisions in critical scenarios is going to face resistance.
So what is required on the technical side by 2040?
By 2040, the system must achieve an obstacle prediction accuracy of 99.9% or higher, and critically, key behavior decision correctness must reach a perfect 100%.
100%.
Now, this doesn't mean the system will never have an accident, but that its planned maneuvers must align perfectly with safe, legal driving practices in every single instance. The trajectory update cycle also has to be extremely short, shortened to 50 milliseconds or less to maintain that responsiveness.
So we've established that E2E is the final architectural destination. Why is this model so crucial for achieving the 2040 goals, particularly in solving those complex, unpredictable scenarios?
It really boils down to efficiency and error mitigation. By mapping raw data directly to control output, E2E avoids the compounded error and the stiffness that was inherent in the old modular system. It enables stronger generalization because the large model learns all driving tasks simultaneously, recognizing patterns across perception, prediction, and control.
It's a holistic approach.
It is. It uses large models for every element, something like UniBAV for unified perception, Waveformer for advanced prediction, and integrated architectures like IDC for control.
To achieve that 100% key behavior correctness, the system must essentially understand the physical world. What are the next big technological breakthroughs required for that?
The focus is squarely on world models. These are sophisticated AI foundation models that enable video prediction while considering the fundamental physics of the environment. Instead of just reacting to the current frame, the system simulates potential futures in real time, choosing the safest path. The goal is a truly universal, autonomous driving foundation model, supported by vast annotation systems that integrate simulation and real-world data seamlessly.
We saw 20 billion parameters targeted for 2035. The quantification of model complexity by 2040 is just remarkable.
By 2040, model parameters are targeted to reach 100 billion or more.
And why such a massive scale?
To host these world models, to ingest and process the full data stream from that car road cloud integration, and to encode the necessary physical and social understanding to achieve superhuman generalization. Concurrently, the vehicle-side computing power needs to reach multiple thousand TOPS level a necessity to run these gigantic models in real time on the edge without relying constantly on cloud processing.
So the ultimate goal here is system performance that surpasses the human level, resulting in an accident rate well below human drivers.
It's the very definition of the superhuman driver.
We've discussed the algorithms and the models. Now we have to turn to the infrastructure that certifies safety at this superhuman scale. Testing and evaluation is vital.
It is. And the core goal is moving to a comprehensive, data-driven system covering the three pillars of testing. You have model-in-the-loop, or MIL, which tests the software algorithms, hardware-in-the-loop, HIL, which tests actual hardware components against simulated environments.
Like the Lab CR Hill systems we mentioned.
Exactly. And finally, vehicle-in-the-loop, or VIL, which involves real-world vehicle testing on test tracks and on open roads.
But the current obstacles are scale and dependence. The scale and diversity of the scene libraries are lacking, and there is that reliance on foreign core tools like NI and DSpace. What is the strategic action plan to overcome this dependence and scale up?
The strategy is twofold, and it's mandated by those self-sufficiency goals. First, accelerate the autonomous R&D of test equipment developing domestic versions of those critical hardware and software tool chains to achieve the 80% self-sufficiency target. Second, building national-level test scenario data centers to facilitate shared data resources. This resource sharing is necessary because no single company can accumulate the required 10 billion kilometers of varied test mileage data by 2040 on its own.
And what are the final ambitious 2040 performance goals for the testing system itself?
The goals are definitive. Scene coverage must be comprehensive, reaching 99% or more of all possible driving scenarios. Test tool self-sufficiency must reach 80% or more, establishing clear independence in the validation process. But I think the most telling metric for the quality of the system is the simulation test defect check-all rate. That must reach 90% or higher.
Explain that check-all rate. What does it signify?
It signifies the fidelity of the simulation environment. If the check-all rate is 90%, it means that 9 out of every 10 defects or potential failure modes found in real-world testing, in VIL, were previously identified and flagged by the simulation environment, by ML or HL. This proves that the virtual testing ground is robust and realistic enough to predict real-world flaws before the physical car ever hits the road, which is absolutely crucial for certifying a superhuman driver. So we've mapped out the technical specifications for the next 20 years. Now we have to look at the non-technical foundations that are required to support this highly quantitative roadmap. The sources identify 4 critical pillars of execution.
Okay, so this moves us from the whiteboard specs to the necessary industrial and human lift required. The first pillar is a continuation of that R&D push, technology breakthrough.
Yes, but with extreme focus. A sustained focus on R&D of the specific cutting-edge AI technologies necessary for the paradigm shift, large models, the E2E architecture, and world models. This requires a dedicated long-term national commitment that treats the autonomous driving stack as a foundational strategic technology, not just another consumer feature.
The second pillar addresses the fundamental fuel source for that E2E architecture, the data ecosystem.
This involves building high-efficiency data closed-loop systems that can ingest the billions of kilometers of data. The imperative here is leveraging generative AI to solve the scarcity of that rare long-tail data, ensuring the E2E models are robust enough to handle the infinite variables of driving. This is an infrastructural and software challenge of immense scale.
Then there is industrial synergy, which is about moving beyond the inherent limits of a single intelligent vehicle.
That is where the crucial importance of rapidly promoting car-road cloud integration infrastructure comes in. Single vehicle intelligence, even with 100 billion parameters, is limited by its local processing power and sensor range. Synergy enables V2X collaborative sensing and decision-making, which is what delivers that promised 1,200-meter detection range and the critical safety redundancies required to hit the 2040 intervention targets. This is a monumental build-out involving public policy, telecommunications, and urban planning.
And finally, translating this entire blueprint into reality requires the right human capital.
The fourth pillar is talent development. This roadmap sits right at the intersection of deep AI theory, high-performance computing, and traditional automotive engineering. It requires systematically cultivating composite talent individuals with both strong theoretical backgrounds in AI and the practical engineering capability to deploy and scale these massive models into real-world production environments. If you don't have the people who can code a 100 billion parameter model and ensure its functional safety in a car, the whole roadmap stalls.
So what does this all mean for you, the listener, whether you're an investor, an engineer, or just someone trying to understand the future of the car?
It means the entire industry is pivoting. It's a recognition that the traditional modular approach has run into an efficiency wall, a technical ceiling. The only way to achieve true L5 safety and superhuman performance is through the total integration enabled by end-to-end AI and the massive data scale that feeds it. The global competition is no longer about who can implement L2 features best. It's about who can build the most robust, self-learning AI foundation model for driving.
The conclusion seems undeniable. The global competition for intelligent driving is now centered on the E2E data-driven AI architecture. This roadmap provides a clear, quantified path toward achieving superhuman driving safety and efficiency by 2040 through massive leaps in perception, decision-making, and testing maturity.
It's a blueprint for statistical perfection.
And this brings us to our final provocative thought for you to consider as you digest these aggressive targets. We've established that by 2040, the system is designed to achieve 99.9% or higher perception accuracy and 100% key behavior correctness, meaning it drives objectively better and safer than any professional human driver.
Right.
So if that level of reliability is reached, the core regulatory challenge will transition entirely. It will no longer be about whether the system is safe enough to operate, but rather how society determines the ethics and liability when a machine, having surpassed human ability, still operates under a framework of human-defined laws.
That's the question. When a machine achieves superhuman performance, who takes responsibility when that 0.1% statistical failure rate happens? The manufacturer, the AI trainer. Or does the very concept of liability need to change when the system is demonstrably safer than the human alternatives? It forces us to redefine what safe truly means when the benchmark is no longer human, but statistical perfection. And that perfection still occasionally fails.
That is a question that will be settled in the next 20 years, not by engineers, but by policymakers and by courts. Thank you for joining us for this deep dive into the intelligent driving technology roadmap to 2040. We hope you feel thoroughly informed about the quantified path to the autonomous future.